Hello, and a very warm welcome to episode 5 of ChemEng Conversations. I'm your host, Ravi Shankar, and it's my pleasure to welcome a very special guest to our show, Professor Geoff Maitland. Now, Professor Maitland has been a long-standing stalwart of the Department of Chemical Engineering here at Imperial College, having served for over 30 years. And to say that his career to date and his achievements are illustrious would be somewhat of an understatement, with numerous prizes, accolades, and high-ranking positions from establishments and prestigious institutions. During his academic career, he's established himself as one of the leading names in the fields of materials science, thermophysics, and energy engineering, with over 7,000 citations to his name. Alongside his tenure at Imperial, he's been highly involved with industrial research pertaining to oil field fluid engineering and energy engineering with the Schlumberger Research Division, for which he's held the positions of head of the department and subsequently Director of Research. After his appointment as Professor of Energy Engineering here at the department at Imperial, he founded and served as a director for the Qatar Carbonates and Carbon Storage Research Center, or QCCSRC, in 2006. This will be one of the focal points of our conversation today, and I think I'll let Geoff do more of the talking on that, being the founder and the expert in this field. In 2014, he served and was appointed as the president of IChemE, the Institution of Chemical Engineers, the largest governing body for chemical engineering in the world. And most recently, Professor Maitland was honored with a CBE for his services to chemical engineering and for driving strong connections between industry and academia during his distinguished career, which is, I'm sure, a big honor for you and also for the department to have such a leading name be recognized for his services. And without further ado, it's our pleasure to welcome Professor Maitland to our show. So thank you for being on the show.
Thanks very much.
Thank you. So congratulations again on the prize. That must be a huge honor for you. So how was the whole process and experience? When did you hear about the news?
Well, it sort of comes out of the blue, although it's not a complete surprise at the new year. You don't just read it in the paper. You get about a month's notice. I got a letter, and I happen to remember the date. It's the 7th of December. I went to my office, and Sarah, my PA, had put my mail on the desk, and there was this rather official-looking envelope, and I opened it to my amazement. And then I read the date, and the letter was dated the 21st of November, and this was the 7th of December, and it said, would you please reply by November the 28th?
Oh my goodness.
I thought, so near yet so far. Anyway, I rang them up and explained Sarah had been on holiday, and I'm very lazy. I don't collect my own post, and I'd forgotten she was away. So anyway, everything was all right.
Everything was okay.
I was relieved to see my name there.
I'm glad to hear.
Yes.
Yeah. And would you say that this is perhaps your proudest achievement in your career?
Probably one of them. I mean, it's nice to be recognised, but you only achieve these things because you work with some amazing people, both students and colleagues, both here at Imperial in my 2 stints here and in industry. So I think this is a recognition of work that I've done in partnership with a lot of people. Sure. And in those partnerships, I've had a lot of proud moments as well.
That's wonderful to hear. And one of the focal points, I guess, alongside your CBE honours would be founding the QCCSRC during your time here at the department. Would you mind explaining for our audience a little bit more about sort of what are the motivation behind that project and how it all came about?
Yeah. Well, I think it's like a lot of things. It happens because several things come together at the same time. I'd been back at Imperial for 2 or 3 years, and when I first came back here, I wanted to work on fossil fuels and how we continue to use them without causing catastrophic climate change. And if we do that, then there's only one real solution, and that is to capture the carbon dioxide and store it in some way and take it out of the atmosphere before it gets there. And so one of the early things I did was with colleagues here and in earth science and engineering, and that's one thing I'm very proud of, that during my time here, that earth science and engineering, chemical engineering now really work hand in glove in lots of these areas and collaborate in a way that they didn't before. And we approached Shell to have a program called Clean Fossil Fuels.
Okay.
And that was to look at how CO2 is stored and how you could use it for enhanced oil recovery in sandstone clastic reservoirs, the sort of reservoirs you've got in the North Sea and the Gulf of Mexico, say. And that was going quite well. And then the opportunity arose then because the people in Qatar, particularly Sheikha Moza, who was the wife of the Emir of Qatar, had been talking with Shell and said that she admired the work that was going on here. And she was a great champion of advancing education and research in Qatar.
Okay.
And she said, I'd rather like something like this to happen in Qatar.
Okay.
And Shell works very closely in Qatar in exploiting the gas fields with Qatar Petroleum and other companies in Qatar. And so they then came back to Imperial College to see what we could put together. And so it was building on our existing expertise that we developed in the original Shell program, a pull from Qatar. And the third factor, I think, was that carbonate reservoirs are very little understood compared with sandstone reservoirs. And they dominate the Middle East and other areas of the world like Brazil. And so scientifically, this was really interesting, that here was an opportunity to both understand carbonate reservoirs in general in more detail, but also how you could use these to store CO2 and whether the capability for enhanced recovery of CO2 was there as well. And so we had lots of discussions, and it was clear that Qatar had great ambition, whereas the Shell project had been about £5 million. This was of order £50 million. This was $70 million, and the exchange rate was a bit different in those days. And so the ambition was to understand this process in fundamental detail, the science and engineering of that, to provide methodologies that would convert this into efficient ways of identifying storage reservoirs. There's lots of issues in terms of capacity, but also safety of storage, and that you're not going to fracture the reservoirs and leak the CO2 away.
Of course.
And also that there was an educational aspect to this, that they wanted to train Qatari students to PhD level so that they could train the next generation of experts in Qatar, in oilfield engineering in general and in this area in particular. And so we were able to combine that into this program. The other thing that they wanted to do was to increase their own R&D capability.
Right.
And so there was a huge investment in capital equipment here, some of which the plan was to take over to Qatar Petroleum's own laboratories over in Doha. And that happened to some extent. It didn't happen as much as we wanted to. The other thing about the project was we were going to have a demonstration project in the field so that we could actually refine the technology through a few iterations of seeing how it worked in practice. And again, that didn't go entirely according to plan, but Qatar have implemented this in different ways, as have Shell. So it was a combination of Qatar, the pull from Qatar. They have the biggest gas field in the world. They have the very high GDP per capita, but they also have the highest carbon footprint per capita. So there was a drive of them to actually become known as a clean fossil fuels region, and that was part of the motivation as well.
I see.
So Imperial College's capability to deliver this enabled us to bring together people from the two departments, science and engineering and chemical engineering, but also people from other departments as well. In a project that lasted 10 years, I said $70 million, and we had over 50 PhDs go through.
Wow.
Until the end of last year when the program came to an end.
I see. And in that time, how have you seen the centre evolve in terms of your key outputs or your goals? Do you feel that it's been a successful venture?
Yes. I think there's various measures, of course. Of success in this. And I'll pick out three, I think. One is in terms of as a training facility, an education facility for both PhDs and postdocs. We were able to, because of the high industrial involvement, attract very high quality students. And they were very motivated to come and work not only with us, but to have interactions with major international companies, particularly Shell. And they were able to do secondments during their PhD to get a taste of what things were like. So I think it was a really good educational experience. And so that, I think, is a good measure of success of that. And in fact, many of our graduates from the PhD program have gone on to work for Shell and other oil and gas majors as a result of this. So that was one thing. A second would be the publication record. I think we were very lucky in that although we were doing applied research to actually be implemented by the companies and they could exploit the intellectual property that we were generating, we were given a relatively free hand to actually do the research that we thought was necessary to give the basic understanding of the rocks, the fluids, not only the CO2, but how they mix with the fluids in the reservoir, how they interact, because CO2 dissolves carbonates under certain pH conditions, so it's a quite complex system. And the program has produced over 200 papers over that time. And so I think in terms of research output and what it's done for the careers of the people involved has been a significant success story as well. And I think the third success was somewhat unexpected. And it's a good example, I think, of how the best research is done in an environment where you have flexibility and you can see opportunities that weren't necessarily there at the start of the project.
But they may arise.
Yeah. And so when we started the project, we had quite a large capital budget. But this was for spectroscopy, thermophysical property measurements, of which myself and Martin Tresler have been very heavily involved. But after a relatively short time, it became clear that a key technology that we hadn't built into the original plan was X-ray imaging, both medical scale CAT scan technology, where you could look at fairly large cores of rock, right down to the emerging technology of micro CT, where you can go right down to the pore scale in rocks and look at the pore level, and you could look at the multi-phase flow of CO2, in this case, supercritical CO2, displacing oil and water in depleted oil and gas reservoirs, or displacing brine in brine saline aquifers. And this turned out to be transformative in what we did. A picture, they say, is better 1,000 words. And once you see what's going on, you understand what physics you need to build into the interpretation of the modelling. My colleague Martin Blunton at Science and Engineering is probably the world leader in pore scale modelling, and this has informed the way that he and his team have been able to develop those models greatly. But you then not only give input to the physics and understand the wetting and the loss of surface interfacial science in this, we can actually measure contact angle on a pore scale. So you can actually go into a micron pore and you can see droplets of oil and water, and you can measure contact angles. So you get a whole distribution over a very small sample. You get hundreds of thousands of contact angles, and you can see that's just one example. But this then provides a test bed. All your models of displacement of CO2 into these small cores, which are you hope are representative of the larger reservoir, you can actually test out not only in a macro sense as how you're displacing the fluid fronts, but right down to the pore scale. And in fact, the way that CO2 is trapped in these reservoirs is not only because of the macroscopic seals of low permeability rock that stop it coming out, but because of capillary trapping.
Right.
That if you pump more water in, you can't displace the CO2 because it's trapped by capillary forces. And then eventually it dissolves in the water in the reservoir, and over long periods of time will actually mineralize to carbonates. And so there's not just one mechanism, it's belt, braces, suspenders, and everything else that will actually keep the CO2 there over the hundreds of years that's needed before it mineralizes, and keep it out of the atmosphere and do it safely. So all this was enabled by us being able to transfer our capital budget to buy a medical CT and a micro CT, which were in the use round the clock and being used for other projects in chemical engineering to actually broaden their application. And so we transformed a very dark dungeon in chemical engineering into this brand new imaging lab, which has in fact paved the way for the project that I currently run with Shell called Digital Rocks, which in fact takes imaging and modelling and applies it more broadly than carbon capture and storage to the way you would characterise reservoirs in general.
Oh, wow, I see. It's very interesting. And now, you mentioned that you've been involved with oil field engineering and sustainable fuel production throughout your career, and you've been trying to balance this use of fossil fuels with mitigating climate change. How have you seen things progress in your field since you've been working on it throughout the years, and where do you think we are in terms of progress? What do we need to do better?
Right. The reason I'm quite passionate about this field, and the reason I wanted to work on it when I came back from Schlumberger to work with a broader range of stakeholders here, is because although we need to remove fossil fuels as quickly as possible to reduce carbon outputs, the rate at which we're going to be able to ramp up renewables to a scale and a cost that will actually address the problem in an environment where the world's population is going up and the demand for energy is going up in a way that it will probably double by 2050. I don't believe we're going to get there simply by hoping that renewables come through fast enough. Many countries have got huge reserves of fossil fuels, and for both economic and security of supply reasons are going to use the coal and the oil anyway.
Sure.
So I think rather than ignoring that problem and hoping it will go away and that renewables will come through faster than is technically feasible, we have to accept the fact we're going to use them and then develop these mitigating mechanisms. So where we've come from and where we're going to, I think, is that we've seen a fantastic increase in the rate of implementation of renewables. That's been helped by a lot of subsidies that have gone in, and that's quite right to get the technology up. But it's starting from a low baseline. So when I first started on this, we probably had about 10% renewables in the world in the mid-2000s. Now, we still only have 20% of the total world's energy. This is very variable, of course, in terms of different parts of the world. France has a low carbon footprint for its GDP because it has a lot of nuclear.
Yes.
New Zealand and Iceland and other countries have a lot of hydroelectric. So, but on average, it's about 20%. So that we've still got to actually we're using a lot of fossil fuels, up to 80% for power, and also industrial processes. Even if you stopped using fossil fuels to power them, a lot of processes like cement and iron and steel, they produce CO2. Yeah. So unless you invent a new industrial process, then you've got to be able to capture that. So the need for carbon capture and storage and in more recent times, whether you can use CO2 as a feedstock, as a small contribution to that. It's about 1% of the CO2 that we need to get rid of. You can use in that way, but it's still it's part of the circular economy of how we can use waste materials like that. Although it's the perception has increased that it needs to have a role. I think until relatively recently, it was still seen as a solution that we may be able to avoid, or as a stopgap solution rather than something we need to use for quite a long time. And I believe that we're going to need to use it well into the second half of this century, and that as we wean ourselves of fossil fuels, not completely, but to the level that we need to, it will play a role there. What you've seen gradually over this period I've been working on it is that you've got more and more projects, not at a very big scale, but demonstration projects to show that the technology is feasible. And one myth of carbon capture and storage is that this is an emerging technology, and it's still this is technology that's been used in the oil and the chemical industries for a long time. Norway has had a project since 1996 in Sleipner, and it's telling that that's the most successful, over 1 million tonnes of CO2 a year, in a country that has a carbon tax. And so this is the thing that's changed over my period looking at this problem, is an awareness that sometimes you've got economic drivers, either where you've got a carbon tax, there aren't many places where that has sustained itself, or where you can use the CO2 to recover more oil and gas to help offset the costs, because that's the problem. When you use CCS, it adds $40, $50 pounds a ton of pounds. It costs that a ton to take out, and that actually then gets passed on in the cost of electricity or the cost of the process and the products. And so governments don't like to hand on taxes like that to the general public. And so what you've got to think of is, how can you get that back? And where there's not a way of monetizing CO2, either by EOR or carbon taxes, or by payments for storing CO2, in the US now they have 45Q, a subsidy that's been introduced for every ton of CO2 that you bury. And this is one of the few things under the Trump administration where I think we've made some progress in this difficult space. And I'd like to see more of that happen elsewhere. What you've got to do is to see how can you actually bring the cost of CCS down to the level where it's affordable and it doesn't add too much cost beyond the normal fluctuations that you get in fuel prices anyway, to the cost of electricity and the cost of products. That's where it's involved in the processes. So a lot of work has gone on, I think, in the last 5 years to actually realise that, in fact, it's not going to be some brand new technology, some super capture technology that brings the cost down by a factor of 10 that's going to do it. You do it the way you actually bring down the cost of all chemical processes, that you actually build it at scale, you learn from putting up large-scale plants, the economies of scale, and how to actually make efficiencies. The second plant probably costs you 60% of the first one, and after 5 plants, you brought the cost down probably to 30, 20% sometimes of the first plant. And then new technology comes through and helps you to actually further squeeze the costs once you've done that. But you've got to make, to some extent, a leap of faith that the existing technology, you can bring this down. And I think in this country and some other countries now, there's an increasing awareness that we have to do this. And there's been some initiatives by oil and gas companies. Chevron Australia has made a huge commitment to big gas in Western Australia to put CCS on that. And in this country, I think there's now an awareness, having had 2 attempts at competitions to actually put CCS in place, which have both failed, because it was seen as below the radar. If you remove the money for these competitions, no one would notice, and that's quite right, because the awareness of the public that you need to do this until fairly recently, I think, was quite small. And so I think we're seeing now a a transition to an era where there's a realization that to meet the carbon budgets, certainly in this country, which has been very good at actually being on track to reduce our emissions to 80% of what they were pre-1990. But to do the next few budgets from 2025 onwards, we're going to have to use carbon capture and storage, and all the models show that. So that's another thing that's changed, is that now all the models of climate change and carbon mitigation scenarios show that all the scenarios to meet the Paris target of 1.5 degrees, or even 2 degrees, you need carbon capture and storage. That all scenarios that don't have it in are more expensive. So CCS is on the lowest cost route to doing it. And in fact, to meet the 1.5 degree scenario, you're going to have it. It's very inefficient because at 400 parts per million, the driving force to absorb things onto adsorbents or solvents is very small. So those technologies are being developed, but they're very expensive at the moment. And so the cheapest bulk way to do it is what's called BECCS, bioenergy with CCS, where you take biofuels to produce power or fire and energize industrial plants. And because those have been produced by photosynthesis from the CO2 in the atmosphere, when you capture the CO2 from those processes, by an indirect route, you're essentially taking the CO2 that's formed those biofuels out of the system and storing it away so that it's taken out of the atmosphere. So I think that's going to be needed in the 40s and 50s of this century. In order for that to happen, you've got to have CCS, and I think people are beginning to realise that this enabling technology has got to be there in order that we can actually meet these targets.
Sure.
And I think there's been a realisation that the developing countries are going to need a lot of help to do this by helping them with the technology, but that's business opportunities for countries that are the first movers in this technology. And we've got to have some distribution of who takes the responsibility for taking the CO2 out of the system over this century. And those that can afford to do it now are the ones that have got to take the lead. And then as the century progresses, then more responsibility first to developing countries, but then get to the point where they're in a position that they're economically in a position to do it themselves. And so you can see there's quite an evolution in thinking here that we're still in the middle of. So, but I'm an optimist, and for me the glass is always half full.
That's good.
I just add one cautionary tale. At the moment, we have 20 large-scale projects in the world, and to meet the target of 10 gigatons per annum of CO2 that we need to take out from fossil fuels by 2050, we'll need about 2,000 projects. So we're a factor of 100 down at the moment, so we've got to move pretty quickly.
Just one final question I wanted to sort of round off the show. It's been very interesting so far, which was having gone through a lot throughout your career, both in industry and academia, and with a lot of experience, what advice would you give to students who are perhaps considering a career in not necessarily chemical engineering or just science in general, or for our students in the department who are studying now already?
Right. Well, I think first of all, getting more and more people at school interested in STEM subjects and going particularly into engineering, is absolutely crucial both for this country and the world, because all the things we've talked about are only going to be solved by engineers of one sort or another, and a lot of them by chemical engineers. So the first thing I would say to young people is that if you have a desire to change the world and to work for good in the world in a positive way and improve the quality of life wherever you are, and you can do this as a practicing engineer or an engineer working in finance or in management, or then engineering, I think, is an excellent platform to do that. And it will open up opportunities for you that you can't imagine when you're studying as an undergraduate. So if you want a platform to do something that's both exciting and good in global terms, then I can't think of a better platform than to go into engineering. The second thing I'd say to people is follow your dreams. Don't be put off by all the barriers that you see. Don't lower your ambitions if you get a few knockbacks, because those are the things that will carry you through. And your education and the environments that you work in will give you different ways to do that. But unless people have vision and want to change things, then things will change incrementally, but they won't necessarily change in a big way. And I don't necessarily always mean science and engineering inventions and things, but the way people think, the way we collaborate together, and the way that you as a team can do far more than you can as individuals. And one of the things I'm most proud of in the teaching area is that with John Perkins, Stephen Richardson and Julie Higgins, we started the first year design project, which still exists in that form, to take first year design out of a sort of rather routine process and show people, when they've only been here a few weeks, that you can in fact do amazing things. You don't need to know all the facts.
Sure.
It's more about how you work together, and working in a team is absolutely crucial. So have some dreams, follow them, but take others with you.
Sure. And
the final thing I'd say to people, lots of, particularly since I've retired, people come and knock on my door and they say, I want to do this in my career, and how do you plan your career? And so the advice I usually give is that it's very difficult to plan your career. You can have a general direction you want to go in, but I always wanted to be an academic, and I was a scientist, then I became an engineer, and then I wasn't an academic, I was an industrialist. I thought I'd be an industrialist till I retired, and then I had this opportunity to come back. So it's all about knowing which doors to go through. In your life, many doors will open and many opportunities will offer themselves. And your career evolves because of the decisions you take about which doors you go through. And this isn't entirely objective, and it's not, there's no formula to do that. Your instincts about how this compares with what you want to do are very important. So as part of that, I said you've got to have vision and don't be dampened down by knockbacks. Likewise with the opportunities, don't always take the safe option. Stretch yourself and walk into the unknown a bit, because that's the way that you find things that you never thought you'd ever see, and give you opportunities to do things that you never realised were there. And that's what I've been lucky enough to do. You sometimes make the wrong decision, but the thing is that don't worry about that. That's all part of the learning process as well. So learn from your mistakes as well as your successes, because they're more valuable as well.
Wow. That was very valuable advice, Geoff. No, for our audience, and particularly for me as well, who's sort of getting towards the end of my PhD and thinking about what the next step would be. So definitely I'll take your advice on board. So it's been a pleasure having Geoff on the show. It's been a very wonderful conversation. That's all the time we have for today. So on behalf of all of my team, I'd like to thank you for being on Cambridge Conversations. It's been a pleasure. And if you'd like to see all of our previous episodes, you can tune into our website and also onto a YouTube channel. All of our previous episodes are there. We'd love to hear from you. If you'd like to get in touch, all of the details are on your screen. You can get in touch with any member of our team using our hashtag CE Conversations, and we'd love to hear from you. So until next time, that's all. Thank you and see you soon.